If we really knew the origin of life, that would be a terrific advance. I cannot believe that life originated in space. My feeling is life can only exist in planetary atmospheres. And how does it get there? How is a planet formed? How are stars formed? All that we know about the composition of stars and planets and comets, we know through the spectrum. It's in that way that, for example, we know that there's a lot of methane in Jupiter, in the atmosphere of Jupiter, and a lot of hydrogen, a great deal of hydrogen, and other similar things, carbon dioxide on Venus. And that was first established by the spectroscope.
Gerhard Herzberg is no ordinary astronomer. He learns about space without looking through a telescope. Instead, he uses spectroscopy. His experiments deal with atoms and molecules. He hunts for clues to their behavior, examines scraps of evidence left behind when matter interacts with light. In 1971, his detective work earned Dr. Herzberg the Nobel Prize in Chemistry.
A scientist, of course, is required to be a logical man, but that doesn't mean that science works always in a logical fashion. Very often, a scientist has some bright idea which he cannot justify at the present time, and then he proceeds to try and prove this idea by logical experiments. I remember a very interesting quote by Professor Calvin of the University of California, who said, "The really creative scientist is one who can intuitively guess the answer when only half the evidence is in and only half of it is right." And I think there's a lot to that.
As a young man, Herzberg studied physics. When he left his native Germany for Canada in 1935, little was known about molecular spectroscopy, but his findings soon brought valuable new insights to the field, and for Herzberg, a worldwide respect among scientists. Today, after more than 30 years of work at the National Research Council in Ottawa, he has lost little of his boyhood fascination with the unknown.
The flow rate is 10 minutes, is a flow rate.
Well, I think spectroscopy is creative just like any other science. And it just intrigues me that there are such things as molecules, and how complicated can they get? Why are molecules the way they are? And what kind of molecules have not been found yet that should be found? So spectroscopy is a science of discovery. And I think it's fair to say that it has made a very basic contribution to the development of science all over. Spectroscopy deals with the analysis of light into its components. The first person to have done that was Isaac Newton, who in a dark room had a hole in a curtain and took a prism and held it in this beam of light that resulted, and he found that the light is decomposed into its various colors, from red to blue. The rainbow colors, in fact, the same phenomenon happens more or less in the rainbow, except there are no prisms. And so Newton was the first to establish that white light is made up of all these various colors, which can be combined again and give again white light, and that all that the prism does is separates out these various colors, which are all contained in the white light.
Today, instead of using prisms to separate light, scientists work with instruments known as diffraction gratings. Light rays are broken up by thousands of very fine parallel lines etched on the surface of a concave mirror. Various wavelengths in the light go off at different angles. Some are deflected less than others. The result is a rainbow of color. By spreading out wavelengths in this way, scientists can examine different areas of the spectrum in detail and look for fine changes in the light caused by atoms or molecules. To do this, they take pictures of the light in a spectrograph, a kind of room-sized scientific camera. In one technique called absorption spectroscopy, light is filtered through a sample of atoms or molecules, usually a gas, contained in a glass tube. Certain wavelengths are removed by the sample, while the rest of the light continues on undisturbed. The beam is then focused by a lens and passes through a narrow slit onto a diffraction grating. Once spread out, the light travels along to another part of the spectrograph, where it hits a photographic plate. Here its image or spectrum is recorded, just as it might be on the film in an ordinary camera. The missing pieces of light removed by the sample show up as a number of tiny gaps or lines in different parts of the spectrum. While spectrographs may not look quite the same in every laboratory, certain elements are always found in absorption experiments. A container of sample, lenses to focus the light, a narrow slit, a diffraction grating, and a photographic plate. Light filters through the sample onto the plate. Its missing wavelengths cut sharp lines in the spectrum. Another method used to study atoms and molecules is called emission spectroscopy. Unlike absorption, an electric current is passed through the sample. This time, the molecules themselves are excited and give off certain wavelengths of light. These so-called emission lines from the sample register on the photographic plate. In the darkroom, emission or absorption lines become visible as the glass plates are developed. Scientists use these black and white lines as keys to unlock the secrets of matter. With spectroscopy, they not only answer the most basic questions of pure research, but can also solve the more practical problems in the industrial laboratory. Measurements of spectral lines provide the clues. The strengths of the lines and their positions in the spectrum tell about the size, shape, and energy makeup of atoms and molecules. Each different sample leaves its own distinctive pattern of lines, a coded message unlike any other.
Spectroscopy is a means of decoding the message that is in the spectrum and transforming it into information about the structure of that particular molecule.
This structure, in fact, determines how molecules respond to light and how they step between various internal levels of energy, arranged like rungs on a ladder. In absorption, molecules remove a portion of light, step up to a higher energy level, and leave a line in the spectrum.
Each molecule is unique in the sense that it has a spectrum of its own, just like every individual has his individual fingerprint.
A molecule's emission fingerprint is just the opposite of absorption. As it drops to a lower level, the molecule gives off energy, which appears as a line in its spectrum. But emission isn't limited to molecules in the laboratory. We see more common examples every day. A diffraction grating brings to life the spectrum of the street. Just as they do on Earth, atoms and molecules in space leave the same fingerprints in their spectral lines, both by emission and absorption. Using modern telescopes to gather light from space, astronomers record these spectra and learn a great deal about the conditions of stars and of planets.
Well, the spectrographs that astronomers use, in principle, are very similar to what we use in the laboratory. The spectrographs are either directly attached to the back of the telescope. That's one version. The other version is that the light is taken out of the telescope and led into a room where there is usually a big spectrograph, which is stationary and doesn't move with the telescope.
Here, astronomers take portraits of starlight. The light collected outside by the telescope's main mirror is directed by a series of smaller mirrors and lenses toward a photographic plate. But before reaching the plate, the light first falls on a diffraction grating where it is spread out into separate wavelengths. The message it carries is then recorded on film. By comparing these spectra with measurements made in the laboratory, astronomers are able to identify certain atoms or molecules in space.
But the spectrum really doesn't only tell us what particular atoms or molecules are present in all these celestial bodies. They also tell us a little more because they tell us what, for example, is the temperature. Because a molecular spectrum changes radically when you change the temperature. And so by looking at the relation of a number of lines of a given molecule, the intensities of these lines, you can tell what is the temperature, for example, on the star, or even in the space between the stars. We also find out about what comets are, and it turns out that the spectra of comets are almost entirely spectra of free radicals.
Free radicals. The words have special meaning for Dr. Herzberg. He has spent long years in his laboratory tracking these elusive scraps of molecules which flit by in an instant. Whether on Earth or in space, they vanish almost as fast as they appear, leaving behind little record of their life.
A free radical is a transient molecule. It lives only for a short time. It is a fraction of a larger molecule. For example, if you take the methane molecule, ordinary gas, methane has the formula CH4. That is, it has one carbon atom and 4 hydrogen atoms, the 4 hydrogen atoms being symmetrically arranged about the one carbon atom. Well, if you split off one hydrogen atom from methane, you get what is called methyl.
Removing one more hydrogen leaves methylene, a tiny fragment made of 2 hydrogen atoms attached to carbon. Like other free radicals, methylene reacts instantly with anything it hits. It may live no more than a millionth of a second. Herzberg searched over 15 years to find its fingerprint, to record its fleeting lifetime in a spectrum. One spring, his patience was finally rewarded.
It was in May 1959, I think it was the 12th of May, I had this, what nowadays is called breakthrough, of really finding the spectrum that I had looked for 15 years, namely the spectrum of methylene, free methylene, CH2. And the moment is still very clear in my memory because I remember it was a very busy day and my technical assistant, Mr. Shoesmith, who helped me a great deal in all my work, he came up, I have a new spectrum for you that you must see. I said, I'm terribly sorry, but I have to go to this seminar. He said, you can't go, you have to see this spectrum. And it was it.
Finding the methylene spectrum was a memorable moment in Herzberg's career. Another moment would come 12 years later in Stockholm, the Nobel Prize, Canada's first in the sciences. In noting his contributions to molecular spectroscopy and the study of free radicals, the Nobel Committee said of Herzberg, "It is quite exceptional that a single individual, however distinguished, can be the leader of a whole area of research of general importance."
On the Nobel medal, whether it's for chemistry or physics or for literature, it says, "It is wonderful to see life enriched by the invention of the arts." In other words, the Nobel people consider science, like physics and chemistry, as part of the arts, and I think they're right in doing so. The real advances in science certainly come from creative individuals of a type not unlike, I would say, artists, painters, musicians, writers. They're all creative in different ways, but they are creative. If you give scientists the freedom to do what they think they can do, then I think you get the maximum yield from the scientists. One tries to do science because it is an intellectual activity that is satisfying. It is something that tells us about who we are, what differentiates man from animal, and all such questions. In other words, we do science not in order to gain practical advantage from it, but in order to foster the advance of the human spirit. The intellectual adventure that is involved in science is the motivating force for scientists. Basic science deals with problems that are entirely intellectual. Why is this so? How far are the stars? How big is the universe? And when did it come into existence? And problems of this sort. And then more down to earth in my own field, why are molecules the way they are? And what kind of molecules have not been found yet that should be found? I think a very good quote in that respect is one from the famous mathematician of the last century, Jacobi, who said, "The sole purpose of science is the glory of the human spirit."